Okay, so the agenda today is we'll have a three presentation, and the agenda I think are well known. And on Thursday we'll have another session. I hope to see you there. Before we start, this is a traditional slide that we always show in ASPEN user group meeting to update you guys who are using ASPEN and where. So this is the latest statistic that we have. For the training classes, this is the again a traditional thing, but I guess we don't have them today, so I skip them. Check the ASPEN website for the latest information for the fall class. Okay, if you need a training more often or on site, I suggest that you connect to one of the certified trainers that we have set up, and the information is on the ASPEN website. And lastly, if you need to get in tech support from ASPEN, here's the email that I always use, because if you email directly to one of us, there's a chance that we are on travel and we may not be able to see you. Okay, so that's the very we'll now have the next presenter to start our real program, and we'll have ASPEN President, Mr. Sherman Chan.
Okay, I'm Sherman Chan, and here let me bring up my presentation. Thank you very much for attending this users group meeting, and I'm Sherman Chan, and I'm going to talk to you about wind and solar plant modeling in ASPEN OneLiner. Okay, I will be talking about two classes of generators. Number one is type 3 wind generator, and number two is a converter interface generator. Now, the number one type 3 generator is a special type of rotating machine where 70% of the power generated goes to the network, and the rest is fed back to the rotor winding through a converter. And by doing this, the wind turbines can be turning at any frequency practically, and you'll be able to still get 60 hertz out of the output. Okay. The second type of wind machine is called type 4 wind plant. Basically, in this kind of okay, so let me also mention that the number two, the type 4 wind plant, also works for solar and machines work mainly from GE, and there are three items here. First, the generator limits its current to roughly 1.2 times full load current during a fault. Secondly, the generator resists outputting negative sequence current. You say, well, why is that? Well, it turns out that if the generator generates negative sequence current, it will cause a ripple in the DC circuit that's between this back-to-back converter that supplies power to the rotor. And then the third is that the generator outputs no zero sequence current, mainly because the terminal of the generator is connected line to line. So there's no way for it to generate a negative zero sequence current. Oops. Okay. So how do you model this type of type 3 wind generator in OneLiner right now in version 14? Well, the answer is that you should use the current limited generator, because we created this model precisely based on that 3-point description that I just showed you in the last slide. And what we do is that if the current is too high, we first try to limit the current by lowering the voltage sources behind the positive sequence source. And then we also try, if not successful, lower the amount of negative sequence current. And these two, we always say, then a lot of you are probably thinking, wait a minute, I don't recall there's ever a negative sequence voltage source in the generator model. Well, there aren't any in the conventional generator, but we added it to this particular model so that we could do this. And so these positive sequence and the negative sequence voltage sources, they coordinate with each other to maintain roughly the same ratio of positive and negative sequence current during this adjustment. And the adjustment, of course, is to lower the current so that they don't violate this maximum current limit. So this is how we have been doing it for quite a few years. Now, in the last 3 years or so, I have been a member of the PSRC working group C24 with the mission of looking at the modeling of these generators, both solar and wind, for utilities in short circuit programs. So what I learned is kind of reflected in the models that are being developed by OneLiners. Okay. So the Type 3 wind plant model, ASPEN and ASPEN funded research at Polytechnique Montreal has developed such a model. And so in version 15, we're going to, we have implemented a new Type 3 wind plant model. So this model was started out as a dynamic model, then through a little bit of fancy footwork, ASPEN was able to change this model to a quasi-steady state model that works with phasors so that it could be used in short circuit program. So we have taken this model from ASPEN, and I'm really grateful for help that ASPEN has given us. So in version 15, the Type 3 wind model is the one that is developed by ASPEN. So we have already benchmarked our model against the ASPEN, and we are close to the second and the third digit in the answer. So we're pretty sure that we're doing the right thing here. Okay, then the Type 3 wind generator also has another special state called crowbar, and I think there's 2 R's in crowbar. So under crowbar, the machine basically shorts out all the rotor windings, and thereby turning the rotating machine into a good old-fashioned induction generator. So when this happens, usually you will get a much higher fall current, up to about 5 times. So if you are simulating, have a plan with this kind of Type 3 wind generator, it's important for you to simulate with this crowbarring turn on so that you can find out what the maximum current is going through your substation equipment. Okay, so let me go now to converter interface generator. This is solar. Remember, this is solar, batteries, and all the other things. Type 4 wind plants, the ones that go 100% of the power goes through the converter. So for now, I suggest you use the voltage control current source, and information on that is in Appendix J of the OneLiner user's manual. It's also in your online help. If you're running OneLiner, press F1 key on your keyboard, and the online help will come out. And Appendix J is in Juliet. We will have this description on how to use it. Okay, so let me talk about what are we doing for this kind of generator in version 15 for the type 4 wind plant and solar? The new generator model has an improved user interface. You don't have to enter those current magnitude and power factor angles anymore. And probably a lot of you are saying hallelujah when you hear this. There are several control modes available: constant power, constant voltage, and dynamic reactive power control. You say, well, what is dynamic reactive power control? Well, we actually used to call that FTP, or fault ride-through control, but we changed its name because ASPEN decided to change the name, and I think it's really a better name, because fault ride-through can be confused with a standard that tells you how long the generator has to stay on during a fault. And so you have three choices: constant power, constant voltage, and reactive power. And behind the scenes, the program would generate all these power factor angles and everything. So you don't have to do that funny footwork anymore. So, and also, there would be an additional Sherman grid code says that for unbalanced fault, the converter has to also inject a negative sequence current roughly 90 degrees away from the negative sequence voltage. What it's trying to do is to imitate what a conventional induction machine will do, and thereby making it possible for the electric utilities to use the good old-fashioned negative sequence relays to protect the generator as well as everything else around it. Okay. You guys don't have any questions at all? I don't see anybody submitting any questions in Slido. Okay, so just to prove to you that everything is working well, this is actually a real simulation that was done with version 15, experimental build of version 15. I have three generators on the right-hand side. I don't think my pointer works. Oh, maybe it does. Can you see my pointer? Anyway, the top generator is a conventional one. Just ignore that for the time being. The middle one is a type 3 wind plant, and the bottom one is a converter interface generator. Now, you notice that there's, for the type 3 wind plant, there's a little 3, it's hard to see, but that tells you that it's a type 3 wind plant. And for the converter interface, there's a letter 4 in the middle of the circle, and that works for converters, solar and type 4 wind plants. Okay, so I'm showing the positive sequence only right now, but if it's an unbalanced fault, type 3 wind plants would usually also contribute negative sequence currents. Okay, so let me go to the next one. I'm showing you some dialog boxes, and this is the dialog box for converter interface generators. So let's start with the picture on the second on the left half, and that's the main dialog box. You get the ones on the right-hand side if you press the advanced settings in the on the main dialog box. So you notice that in this dialog box there are in this dialog box there are number units. And what we are trying to do is to encourage the aggregation of the units rather than modeling 10 different units. For example, if you just put the number unit equal to 10, and that would save the program a lot of work and also save you a lot of work. And and then you say, well, what about that collection network? You tell me I don't have to model that. Well, the answer is that for the utility people, 99 out of 100 times, I bet that you probably do not have to model the collection network, because they really, and there are studies that have proven that you don't have, it isn't necessary. Okay, so okay, let me go to then well, I don't want to get into too much in the nitty-gritties. But you notice that everything it has been already implemented. Okay, and then this picture, I believe, no, there's only one other slide. This is the type 3 wind generator. And again, that there's a number of units on the left-hand side of the dialog box. That's the main dialog box. And now on the right-hand side, you see a lot of parameters, and that may scare you at first. But the ones that are most difficult to get often are the machine parameters in per unit. Well, what we have here under that machine parameters in per unit are the typical parameters of an induction machine that's rated, several megawatts. So you can, for most people, you can just keep this stuff on the advanced setting and never look there, and you'll be a happier person. And also, on the left half of the main dialog box, notice that about 3/4 of the way down, there's a little checkbox called crowbar. Again, I only spell it with one R. I hope that's one last. We don't know 100% for sure yet, but it's unlikely. And we have already some tests that shows that they won't, but I'm not 100% sure. So for those of you who are going to model these generators, I suggest you go back and see if you can get your short circuit set up to work with start from linear network equations. So this is the end of my presentation, and I see there's still several minutes, so I can, if you enter your questions into Slido, I can answer them. Nobody? Okay. Well, then I'm finished.
Okay. This is Thanh Nguyen again, and this is my turn to show some presentation here. In my presentation, I will tell you about what you can do more with ASPEN OneLiner, which I am hoping that you're already making a lot of use out of that, but there's things in the program that I hope I can show you today that you have you most use it better. Okay. So the topic is about automation and scripting in ASPEN OneLiner. And the purpose of that is if you are willing to do some or sometimes a lot of programming, then you can use this tool to get OneLiner and load flow, to get work done faster, avoid mistakes in all the things you do with OneLiner and PowerFlow, like calculation, simulation, compliance, and other things. And you can even enable new kind of study that was not possible before, which we will see in a concrete example later on. Okay, so what is available in OneLiner? What is available is a very powerful scripting engine. We name it PowerScript, and with that power scripting engine, you can make the program almost do anything you want. Almost, maybe not anything, but a lot of things that you want. And also the program can also have, if I have time near the end of the presentation today, and also show you some additional feature that require less of programming, but again, it also can let you automate what you need to do with OneLiner. Okay, so the ASPEN PowerScript is built into every installation of OneLiner, and it has on the all kind of access to your OneLiner PowerFlow network and relay data. It will let you execute OneLiner and PowerFlow calculation and so on. And it also will let you do external programming stuff as well. So the scripting engine, of course, is programmable with either built-in scripting language that comes with OneLiner, and that's the VBA-like. And other way to do the programming for the PowerScript is with the latest module that we have added to the programs that's shipping with OneLiner v14.7 OlxAPI, and we will show you a little bit more about that later. Okay, so the scripting engine operation, you can run the script through the engine either inside OneLiner, and the way to do that is to go to tool scripting and run the script program you want. Or you can also, if you have one that you run very often, you can assign that to the tool user-defined command. Okay, let me see if any questions for on Slido. No, not yet. Okay, so the external application can also, with that OlxAPI module, can call the scripting engine and make it work now. And we example on that later on. Okay. Okay, so before I show you some more about the detail, let me just go ahead and do some example. Okay, and let me see, here's my OneLiner, and hopefully I can share that. Let me share OneLiner. Okay, so I was about to demo how you run a script. You can use this button and select the script you want to run. If you run it before, you can use one of those buttons here to find the one that you want to run and say run. Please select a relay group. Let's select a relay group and this one. Okay. You can see that when you click something, the script knows that which object you are clicking on. So if I click on another bus and run a script, it's telling me that I selected a line between Tennessee and Nevada, and it automatically retrieves the impedance of the line. It also tells me that the ratings are all 0. Let's double check if it is this. Yes. So that tells you that the a script can read all the data that you have on the screen. It knows which thing to read. Now it can also do things like run the fault simulation. Okay. Now the script just run the simulation of one line to ground fault here, and that is what the script can do. You can run simulation, and it can also do things like getting the result of that information of the simulation. So you know that if you put a little bit of the programming here, you can make it do all kind of things that you want. And in this example, what I have been showing you is how you can use the script to operate the OneLiner from within. Now let's just leave this thing here and see if we can do another demo for the kind of action that can come from outside. So here's my, you see shortly a command line windows from outside. Okay, let me go to where I have that demo. Just give me a second here, and I need to navigate to where I have those files, and let's take just a short minute here. Okay, so I'm almost there. So you see, I going to a folder where I have some Python application, and in this Python application, it has a folder here called lines. Is where I have an example for the Python. And this is a Python program that's supposed to let you open some text, some OneLiner file and do something with it. Okay, so in this example, I have to go and open that file. But here I don't have to. I will ask Python to go ahead and open the file and do something. Let's see what it can do. Okay. So what it's saying that it can report the total line impedance. Okay. And it will let you enter what's the line from and bus KV. So I just run again. So let's see if I want to see how much the impedance of this line between Tennessee and Nevada. All I need to, for this application, I need to just say the file name is sample 30 OLR, which is I tell the script to open the sample 30, and I tell him that use the bus name of Claytor. I don't have this is application has been written in such a way that if you just enter a few letters of the bus name, it will find it and then report it to you. Okay, so what had happened is that the Python program had just opened the this file. It's done through an ASPEN module called OlxAPI, and once after it's opened the file, it finds the bus which starts with CLA, and then it will report the line impedance of all the line going out of it. Okay, so, and then it can even add those tab line together to give you the whole line impedance, for example, in here, okay, and in here. So you can see in this example, again, with some programming with the scripting engine, you can do a lot with this application. Okay, so let me go further to my presentation here. Let's see where I was. No. Okay. This PowerPoint is not showing again. Okay. The built-in scripting language that you need to use is VBA-like, but for the reference online, you can always go to that web page there, or the reference. So it's put it in every copy of OneLiner. For the OlxAPI module, it's been shipped with the OneLiner version 14.6, but the version we are shipping is a so-called development build. We want to get it out there so that the developer can get a hand on it and start using it until the official release will be there later this year in version 15. Okay. The API are callable in Python, Visual C++, and other things. And the reference that you need to use will be the same as the PowerScript. Okay. on the application that you can use a scripting engine for. Those are the very sample, very short list of example that can be used. So what I want to do next is I understand that programming is not for everyone. We all engineer, we know some programming, but sometimes not a lot. So even with that, you can still make use of this scripting feature, because OneLiner, when we ship it, we included with the program a huge library of all kinds of scripting programs that are actually doing very useful work. And I would like to spend a little bit of time today to show you that some of the library application, because in my experience, working with script is done the best. Working with programming in general is done best if you have example. Okay, but before I do that, let's see any question on Slido. Okay, so can we request the scripting for a particular template for a particular simulation? Yeah, I think I'm about to address that. I'm showing you the library that we have shipped, and I highlight a few applications. And the library is open, the code is open, and you can use that as a template anytime. Okay, so that and. Are you going to make a comprehensive manual from 0 to hero, or because currently it's limited? Yes, of course, as a programmer, I understand that the documentation for this is crucial, and we will be working on that. But bear with us. We will get there, but we can make up for what is a shortfall by if you just calling us or send an email to support. You can expect a response within 24 hours. Whether or not we can answer your question completely, we cannot promise, but you will hear back from someone within 24 hours. Okay. Okay, then let me switch to OneLiner one more time and show you some example of the scripting. Okay, here's OneLiner. Okay, so when you install OneLiner, if you hit the script manager button, it will show, it will automatically look for and find all the script that came with the program. And where are those scripts? This says two location that you can find either in the signed up program directory, or it's also could be in the library directory. Okay, so I'll try to highlight a few here. First one, let's say one of the very popular, not popular but important tasks that online that protection engineer have to perform before setting the relay is to find out if the line is short or long in terms of electrical feature, and the indicator whether the line is short or long is calculated with a parameter called source to line impedance ratio, SIR. And in order, the OneLiner can always, when you run the fault simulation, it will calculate source impedance and so on, but then you have to do that manually. That's very tedious. OneLiner, when you it's shipped with a script called SIR. Okay, and this is one of the things here. You see it here, but since I run it before, so it will list it here. And here's where the program is. And here's how you can calculate the SIR correctly. And here are the code, which is if you click edit, you should be able to see it. Okay. Now, let me just run it and see what it's doing, SIR. It's because I selected a bus here, is show all the line coming out of this bus. And if I select the onto Claytor, it's telling me that the SIR for this one, if a three phase is 1.3 and single line to ground is 1.2. Okay, so that's it. And if you want to see how it's done, just open the script and see the code. Okay, now and I must say that this calculation is so popular. It actually has been made a internal command in the latest program already, and it's called source SIR calculator. Okay, so if you run 14.8, you don't need to run script, but if you are running any further an older version, try that SIR. Okay, so another example I want to show you in the term of the scripting application that came with the ASPEN program is this. Okay, so you will all know this, right? So this is a data browser where you can show things in table. And for example, for the line table like this, you see all this R and X and the length and so on. And the question always is wondering whether you can change those numbers in the table like and push it back here. Okay, so that's a long-term plan. We can we'll make it working, but you don't have to wait for ASPEN to act later on. There's already script for that. Okay, so first step you need to do is to export all this number in Excel. Let me see if I already saved it here, so I cannot just override it. Okay, here's the Excel. Hold on, let me bring it up here. Excel table with all this data. So I can say if I want to update a few lines, then I just erase the rest of it. And say if I want to update this number to something and this number to something else, and this I act it accordingly. Then I can save this Excel file to a separate network book, and then say lines update Z. Okay, so this has the new data. Okay, so let me just move it aside. Now there's a script now you can run in the script library. You will find it under a common section. It's called data WKS, data worksheet. It reads the Excel file in the format that you have from the data browser table, and it will compare those data to the existing data, and if they're different, it will update it. So in this case, I expect 2-line impedance will be updated when I run this script. Okay, so I say run this script. Look for that Excel file. Okay, 2 records have been updated. Okay. This is the first record and the second. And let's check if the Claytor to Tennessee. Claytor to Tennessee, this line. Supposed to have 1.57 and 1557, and they are here. Okay, so that's the second script program that I would like to show you. And I guess we'll have a very big demo today, right after my presentation, for the much more complicated script. But I guess I leave that for the next speaker. Let me see if there are any questions first. Slido. Is there a script to update mutual impedance similar to the one you are showing? Yes, I think there is something on mutual, either it should be, I think it should be something mu pair or something like that. Okay, so I think this one is for retrieve the mutual data, but there are some other things. So most of the time, what you may have to do is to stitch together different example from this list, and then because the code is open, you can just try to stitch them together and make them work. And if you have run into problem, call ASPEN or contact ASPEN support, and we can we'll be very happy to help you with that. Okay, let's see. Is there another question here? Is the SIR based on the voltage divider method? I think the SIR formula is comes from, I think, the SCL paper by Thompson, I think. Okay. You can you have a copy of it, and so let's see. Do you have a script to do batch import relay setting from native file format? That's a separate topic. The import. Well, in order to import the relay setting, yes, you can read that in the script. Update the relay setting, yes, you can update that. But there's also a better way and a more comprehensive way to import relay setting through a separate library that we call the RDBI, the Relay Data Interchange. But that is another, I guess, topic that we may not have time to cover today. I'll see if we can come back on Thursday and talk some more about that. Okay, and okay, so is there a way to generate a report to show all the weak source terminal in ASPEN? Yes, I don't see why why not, but I don't remember seeing one of those things exactly already, but there are already some that I think some of the bus fault summary, for example, already go and do for calculation in all the buses and some of those, so we can just stitch that to the exact logic that determine what's the weak source, which is to compare the line to source impedance and so on, and then you can print that report. It's a bit more work, but I think that's, again, is quite possible. Okay, now let me introduce you to one more way to get the scripting done. We have ASPEN has a so-called GitHub location. I'm sure you guys know about GitHub, right? That is where all the source code on the internet is being shared and collaborated and so on. It's one of the several big repository, and ASPEN is there. If you go to that location, you will see that there's already open source 3 section of the code. One is for the Python API sample. The other is the library of the PowerScript program that I show you, so the PowerScript library, we always ship with the latest ASPEN version, but whatever later in between release, we'll push it up here. So always check the GitHub or ASPEN GitHub to get the latest. And also there's a sample C++ code for the OlxAPI program, and more will be coming. So check this. And what's the best is with GitHub, you can easily ask questions, exchange your question or concern with ASPEN developers and also with other people who are doing it. And last but not least, you will have a chance to also contribute to the library, and all the contribution will be open source, and we'll of course acknowledge the contribution accordingly. And then people will see that this code came from you and this application came from you. Okay, so that's the big incentive there. Okay, and there's one more resource that you can subscribe to. I show that in the second bullet here. Do the subscribe ASPEN DEV email, and you will be signed up for in a mailing list where already a couple of dozens ASPEN developers on it, both internal ASPEN engineers and also external ASPEN users are there. And that's this is where you can ask any question regarding to the suite script development. You ask question why it's not working, and someone there, either from ASPEN or from outside who has seen that before, will probably explain that to you. Okay, so that's that last question, last an item here that I want to introduce. Let's go back to Slido to see any. Okay, so how often do you update the file for the OlxAPI? By the way, we had decided to rename it, to drop the R there, so it's just the OlxAPI. Sorry, and then that's should be the final name. Okay. The GitHub, the public GitHub will be updated less frequently because we want to make sure everything there's latest and greatest. It will be, I think, between a month or so. But if you want the cutting edge or bleeding edge or whatever you call it, you want to write to ASPEN support, and we will sign you up with your private GitHub where we push that every week. Okay, and then that's the latest that you can have from there. Okay, I guess that's the last questions that I will hear, and I thank you for your attention. I think I will be done here. Nathan, you're on.
Okay. So hi, my name is Nathan Thomas. I am the co-founder of SynchroSoft, which is the software and automation division of SynchroGrid. I'll talk about what we do in this presentation, give you a brief overview of the company and our products and offerings, and then I'll get into some exciting work we're doing with the ASPEN APIs, both with PowerScript and now increasingly with OlxAPI. The work I'm going to present today is joint work with Luke Hankins, who is a protection engineer who we're slowly trying to turn into a software developer, and Joe Perez, who's the founder of SynchroGrid and also a protection engineer. So here's my outline for the presentation today. We're going to introduce SynchroGrid, just give a brief update on developments since the last Georgia Tech conference, the last time we presented to a large amount of people here. Then I'm going to give an overview of a framework we've developed to auto-tune time directional overcurrent relays for wide area coordination. I'll give some experimental results, and then I'll talk about current and future work along those lines. So SynchroGrid is a Texas-based company that offers a variety of both engineering and software solutions, and we're servicing the entire protection and control arena through generation, transmission, and distribution areas. We're in College Station, Texas. We're about 2 miles down the road from one of the major universities in the state, Texas A&M University. And we have about 20 employees, which is a mix of both electrical engineers and computer scientists. And we've got customers here in Texas as well as others that are listed there. So our core focus is protection and control for transmission and generation. The core focus that we have is in relay setting development as well as setting coordination studies. But we also do relay panel design, third-party review of relay settings, and as well as automating and helping utilities define system protection processes. We're active in NERC compliance operations and studies, misoperation reports, as well as all of the studies that are there listed. And our overall arching goal is achieving simplicity in system protection, mainly because that's what interacts with ASPEN. And the overarching goal is to streamline relay settings development by using automation. And the key idea that we have is we have intelligent templates, which you'll see in the demo look a lot like a MathCAD worksheet that allows utilities to specify their protection standard or philosophy. And the nice feature about it is it's an open-ended language of different types of information you might want to get from ASPEN, line impedances, shortest remote line calculations, as well as different fault study regimens, that it's an open-ended system that you can create these templates and expand and evolve them without us having to be involved as time goes on. And it utilizes the application programming interfaces of ASPEN. We have traditionally used PowerScript. We are in the process now with OlxAPI, which Thanh just talked about. We're transitioning internally to that. And so we automatically generate the PowerScript files from a high-level specification, and then we call ASPEN and present the data back. We're working increasingly with a lot of utilities to address BRC 27 compliance. We have a relay settings development module, which is what we'll show today, that is wonderful for addressing R1 compliance and helping standardize a process for relay settings development. And then we also have a wide area coordination module that addresses R2, which has both big data visualization and then a interface to interactively resolve coordination violations. And all along interacting with ASPEN to verify that changes that are made to relay settings are in fact coordinated. And then finally, we work with the consulting side of the company, combining computer science and system protection expertise to provide consulting solutions that are efficient, accurate, and cost effective. So this is just a high level overview of how SARA works. So we have this notion of a card, and each card corresponds to a relay setting. And you'll see here, over here on the right, if you can see my cursor, this is just defining the impedance of the primary line. And this term here, PLZ1 mag, is a term that's defined within SARA, and then it will have a little micro algorithm, a little script will be generated to actually sum up the different sections of the primary line hopping across tap buses to find the impedance. So the user defines this equation, and then you specify this template along with your ASPEN case and define the local and remote bus. And then SARA will extract ASPEN data. In this case, it's impedances. In other cases, there might be fault studies with contingencies, N-1, the generator contingencies, et cetera. And it's going to calculate the settings and automatically put it up there in the right. You can see that's the calculated setting. Now, this is just the first cut of the settings. We're applying whatever your standard philosophy is. Of course, there's going to have to be a review and adjustment by the engineer based on their domain knowledge. But our goal is to remove the cut and paste and adjust them and then directly export to a relay configuration file. And SARA also will generate a customized Word or Excel report. So here's just a little bit more complicated card, and you can see that it's very similar in the way that it appears. You have an if statement here. If the system voltage is greater than 200, use 12, else use 20, and that's wrapped within an additional check. And the difference being that this will be automatically populated by interacting with ASPEN. And this is what a SARA template looks like, but I'm going to hand this off right now to my colleague, Luke Hankins, who's here with me, who's going to run you through just a quick few-minute demo of doing a line application in SARA.
Okay, so this is what the home screen looks like. This is where you identify your OLR, and this over here is where you identify your philosophy. So let's just peek in here really quick and see what that looks like. So we have a couple tabs here. The first one is allowing you to specify your faults. Now this is going to allow you to specify a fault on the primary line, remote line, a combination of remote lines, or nearby equipment. And as well as flexibility with the location, you can also have flexibility with the different contingency types. You have your standard N-1, N-2, but then you also have the ability to take neutral lines out and so on. And so basically you're going to go through and create all these faults, all the faults that are relevant to you, to the settings that you're creating, and they come over here as F1 and F2 and F3, and you're later going to be able to use them in your equations. And so this is what a philosophy looks like that's complete. And so this is where the core of the company's philosophy resides, basically. So equations can be made specific to the utilities philosophy, and they are completely customizable. We just got done talking about the variables such as PLZ1 mag and SRLZ1 mag. And so, like Nathan said, there's little micro scripts behind these that will compute values regardless of what line you use. So going back to the home screen, after you've got your philosophy settled and your OLR is defined, you can come over here and press Run Template. And this is the part where we start communicating with ASPEN. We're passing these scripts behind the scenes. And then the first one that just happened there grabs all the substations out of that OLR to enable you to define what your local bus is. This next one here is going to find all of the possible remote buses based on the local bus that you just chose. And then finally, we're showing all the possible lines in between the two buses you selected. So if there are parallel lines, you'll see them both here. In this case, there's only one, and you can see that it's multi-segmented here with 2 taps. So by pressing this and then hitting compute, the meat of the calculations is going to happen. We're going to be retrieving all those impedances as well as performing all those fault studies in addition to the contingencies that were needed. And in this last screen here is where you need to enter just a few values that either aren't typically found in ASPEN, or maybe the user hasn't entered them in ASPEN yet if it's a brand new project they're doing. And so you enter those few values and you press compute, and the first screen here after computing the settings is a dump of all the information that was found automatically in ASPEN. So the impedance of the primary line, of the remote and source lines, the transformers, all the relevant information here, characteristic and an apparent impedance. And then down toward the bottom here, we see all the faults that were specified. We get currents and impedances for all the faults, as well as if there was a contingency attached to the faults, it's actually going to tell you what line was found to be the worst case scenario if removed. And so moving on to this relay settings tab, this is what we already saw, except for now the equations have been populated with values and the equations have been evaluated, and you can see final results appear at the top right. And so there's a couple things you can do here on this page. You can click an equation, as I just did, to show the values that were populated. Each card is going to have a section to add comments, as well as the ability to override a setting if it's necessary. So you would add a justification and override the value that Sarah automatically calculated. And so the engineer would typically spend the majority of their time here on this page, checking everything, adding comments and documentation as needed. And then the final step here is the settings summary tab, which shows an overview of all the settings that were calculated. So you can see all that information, and you can, from here, save the project, which is going to save all the values that were calculated, as well as your comments and other documentation, to where you can open it right back up later. You can export to the relay settings file, or you can generate a report that's customizable to however you want to look. And typically, most utilities will make it look like their existing documentation.
All right, thank you, Luke. Are there any questions on that before I move forward? All right, so I'm going to continue on. So, and to clarify, this is all made possible. All of the fault studies, all of the topology information is coming from ASPEN. Luke has become quite a good PowerScript programmer. This stuff is automatically generated based on your philosophy, and all of the fault studies, all the topology information is coming through the various APIs that ASPEN provides. So what's new? We're currently shipping version 2. Since Georgia Tech last year, we've expanded 3-terminal line support, mainly because we have some customers now who have a large number of these. We've also extended our coordination visualizations to support 3-terminal lines. We've expanded fault support. We've added support for split bus calculations. Sarah will automatically go in and split the bus to model breaker failure. And we are looking to release version 3 in a early this summer, roughly June, mid-June is what we're targeting. There'll be a complete user interface refresh. We're integrating coordination into the settings process, so there'll be mode plots and TOC plots. And what's nice about those is those will be dynamic, so they will automatically adjust. You can update the values, and this is where we're transitioning to OlxAPI, the interface that Thanh talked about, because it allows us to do much more fine-grained, dynamic interactions with ASPEN. So we can update one relay setting, rerun a local coordination, and get the result back in a very seamless manner. So we're also expanding consulting services that are accelerated by automation. Again, taking our protection and expertise and our Sarah technology. We've have 3 recent PRC 27 wide area coordination studies that we've done. We've done one for CTT and Rayburn Electric here in Texas. We finished those late last year, and we're currently doing one for Farmington Electric. The Farmington one is interesting. We're helping them not only do the wide area coordination study, but also establish the requirement 1 process. And then since we have this automation through Sarah, we're recalculating relay settings for every relay in the grid, and are going to do a characterization of how relay settings have changed over time and based on the adopted protection philosophy. And again, all of this uses the APIs, PowerScript, and increasingly OlxAPI. And we also do custom protection software. So ABB asked us last year to help them write a translation tool, and we also have several utilities who've come in and asked us, hey, in addition to Sarah, we would like for you to help us automate some of our internal processes, our workflow. So we're able to help utilities with that as well. So I'm going to talk now. I'm going to transition into the main focus of the presentation, which is a framework for auto-tuning time directional overcurrent relays. This was a paper that we published last year at the Texas A&M Relay Conference, and it makes extensive use of the ASPEN APIs. We extract grid topology, primary and backup pairs, and Sarah actually can either use the primary and backup pairs as defined in ASPEN, or it can automatically detect those for you. It, of course, does all the fault analysis in ASPEN, and then uses ASPEN to verify a coordination solution once it's found one. And we initially did this with PowerScript. You'll see that reference in some of the slides, but this was our first foray into using OlxAPI. So wide area coordination is the analysis is the evaluation of protective device selectivity and sensitivity at a system level with the goal of improving reliability. It's a quote from Barman in 2014. We all know it's very labor intensive and it's difficult, and a lot of tools, ASPEN being the king of them, exists to verify coordination solutions, but less work has been done to automate the development of coordinated relay settings or to fix violations that are found piecewise. And with PRC 27 on the horizon, this is becoming an increasingly important topic. Wide area coordination studies will need to be performed more often. And of course, as the topology of the grid changes more often with distributed generation and other factors. So we chose to focus on directional time over current relays first. They play a key role in system protection and the redundancy of the system. Unlike distance elements, they're not affected by impedance-based faults, and they do provide better sensitivity in some cases over distance elements. And different utilities have different approaches to calculating pickups and time dials, but they all have to find proper coordination in order to assure reliability of the system and avoid misoperations. The existing approaches, for the most part, although there may be some automation to check the coordination and even to do a first cut of values, it's inherently manual and it requires a lot of iterative adjustment of the settings by the engineer. And at the end of the day, you have to choose the pickup, the time dial, and curves. So this is a small system. This was taken from the paper that's cited down there. That's a tightly coupled system. So the blue is the primary relay, the red is the backup relay. And so you set those two, ensure they have coordination. You go down the line, ensure you have coordination between those pairs. Here you have two primaries with one backup that you need to do coordination for. And lo and behold, you're back having to look at the setting for relay 1, which is up here on the left. And the settings that you had previously set for it may not provide proper CTI with the primary elements, the primary relays, excuse me, here at 3 and 4. So that requires you then to reevaluate the setting you had done, and you have to, again, go through the cycle. And you just iterate and iterate and iterate until you find a solution. And even if you find a solution, you don't know if it was the best that could have been done. So what is our approach? Our approach is to use an auto tuner, which is a term often used in bidders for a given problem. And we will use this to quickly create coordinated relay settings based on guidance from the engineer. And I give a few sites on the coming paper, but we draw heavily on the academic research that's been done. This is, I think I went back as far as the 1960s where people were proposing the use of computers to automatically coordinate relay settings. And there was a lot of work done in the 80s. But for various reasons, I think immaturity of fundamental computer science research, as well as limitations on computational architectures at the time, it did not come to fruition and become a viable solution for the industry. So we draw from that and then extend it for real world grids, and also taking into account some of the modern advances that are available to us today. And so we remove the tedious manual settings adjustment, allow the engineer to rapidly test different coordination strategies. That may be different CTI requirements, that may be different fault regimens that they want to ensure coordination for. And this is really based on the automation foundation that we laid in interacting with ASPEN through PowerScript and then now OlxAPI. First of all, a paper here that's listed in 2017 where we talked about relay settings development, and then the second paper that talked about our approach at coordination verification, that's the basis for our PRC27 module, a binary coordination module. So I've just given a small sampling of the work that's been done here. There's a large amount. I probably have downloaded and at least read through 100 to 200 papers. And those two surveys at the top are good for getting a good overview if this is something that's of interest to you. But we chose to go with an optimization theory formulation that draws heavily on a seminal paper in 1988 from Erdonade, and a follow-up paper by Burla, and then a more recent paper that formulated it in a way that makes it amiable for use within modern numerical libraries, Damchi in 2018. And there's other approaches, generic algorithms, reinforcement learnings, graph theory. It basically any AI or machine learning technique that's interesting in the field right now is used for has been used to attempt to solve this problem. So someone asked me, where can you read these papers that were referenced? These should all be, if you can screenshot, or if you want to send me an email afterwards, I can send you the full references. These should all be available in the IEEE library. And if not, I can send you the copies I So this is an overview of the auto-tuning coordination workflow that we have. This is a block diagram. So you have the project inception. You define the parameter constraints. You know, my pickup has to be between this lower bound and this upper bound. My time dials have to be with this. These are the curves I'm going to allow to use. And you're going to feed that into this setting selection framework. It's going to grab the input from there, but it's also going to grab the input from ASPEN using the programmatic APIs. And it's going to grab the backup and relay pairs, run fault studies to get the fault currents that are seen both at the backup and relay, and use all of that to feed into a learner that is a settings generator. And all of this internally, there's going to be a refinement that's done by the software automatically verifying. It's going to come up with some tests, candidate relay settings, see if coordination is verified. If not, go back to the drawing board, try again. And eventually, once it has something that it thinks is a good solution, it's going to propose this back to the engineer and say, this is what I found. You know, maybe it will come back and say, hey, I've proven that within the constraints you give me, there isn't proper coordination. Perhaps this is how I think you should relax it, or please tell me how I can relax this so that I can get a viable solution. And then once that's done, we perhaps go through this loop several times. We complete the project with coordinated settings. So as I said, those are the papers that we use. That's the verifier, which is using ASPEN coordination is used. This is, again, our paper for our PRC 27 module. And this work was originally done with ASPEN 14.6. We're using the latest build now. And this is not a meaty supercomputer that we're using for this. This is a laptop with 8 gigs of RAM. We tested 3 real-world systems, 1 real-world system and 2 actually, they're the ASPEN sample cases. I'll show you the 9 bus here in a second. So our tuning requirement is TI restrictions, but respond to a close-in fault as quickly as possible.
Be able for that specifically first one.
Let's talk about the ASPEN one.
Okay. And the input selectors, this is the information it provides. And we gave it learning information. We gave it close-in, open, close-in, and line-in faults to allow it to it. And it's going to use that to create the model and verify that for those fault regimen, proper coordination is achieved. So this is the ASPEN synthetic 9-bus system. There's 18 relays, 9 buses, and we require as part of our fault regimen, we require all backup relays to respond to line-in faults on their remote lines on the primary line. And this is just a sampling of, this is the range, is the upper and lower bound that we allowed users to choose from. Some of these, to be honest, no one probably are not going to set the pickup or the time dial pickup, especially that low. But anyways, in that case, this is what we use for this regimen. So here's the OneLiner case. And what you see here is the results. This is the computed pickup, the time dial, and then here is the response time in seconds to that line in fault. All of the relay fault times are pretty fast, below a second. And we probably would actually in real life slow it down in order to allow the response of the zone 2 element. Coordination was verified, and this entire computation took about 30 seconds. So the real world system is a much more complex system. It has parallel lines. This is a utility here in the United States. And the area of the system we're looking at has parallel lines, each that are 100-mile longs. And it's interconnected, so you have to deal with that additional level of difficulty, right? Is that you can't make settings forever into the interconnected utilities. You have to try to solve the coordination problem internally. Similar parameters were chosen. Here is the real-world system. Here are those parallel lines. And initially, it returned back real quick, the learner did, and said, there isn't a solution, right? I can't reach my protection all the way down those long parallel lines and actually define proper coordination. So the engineer, in this case, we made a decision to allow it to only respond part way down the line. It only was forced to respond to a 10% intermediate fault down those long lines. And that may or may not be something you would want to do in the real world, but this was just an example of how we could communicate to the learner some refined problem definitions. It's a simple change. We reran it, and here are the results that we get. All right, so more recently, we've added contingency support. We've added curve selection. It'll actually compute the curves, support for different philosophies, different approaches to setting the pickups. We model pilot schemes, and we have different optimization goals. For instance, in the real world, you may want to find a coordination that minimizes the number of relays that need to be updated. And we're working to scale this up to a larger number of terminals right now, especially with the contingencies. We only support about 30 terminals, but we are moving into higher performance computing regimens and employing parallel processing, and I think we'll be able to scale up into the thousands of terminals. And we're also going to scale this down. One of our clients has asked us to just do a small local area coordination for their 67N elements. And we're also working on TOC distance co-coordination simultaneous. And we're using OlxAPI as a dynamic analysis ability, again, to be able to do some more advanced things such as sequential tripping. And we are working on a follow-up paper. There was supposed to be one at the A&M conference this year, but it was unfortunately canceled. So what are the benefits of OlxAPI? Being able to move and invoke OlxAPI from a more modern programming language allows you to scale up to a much larger code base and maintain it. We've chosen to use C++, but as Tana said, you can use C#, you can use Python. It's a much more flexible environment. It allows us to make finer grained calls into ASPEN for more dynamic simulations, and it allows you to use debuggers and other tools that really allow you to increase the pace of innovation. And so just some tips from what we've learned is the transitioning from OlxAPI from PowerScript is pretty straightforward because the API is fundamentally the same. Just pick whatever programming environment you're most comfortable with, and define a strategy to test it as you move code over. We did find some bugs as we went along. So wrapping up, how can you get involved with us? Try out Sarah. We're glad to do a WebEx demo for companies. We can provide a sample implementation of your protection philosophy and allow you to test drive Sarah. If you have an area of your grid that you're having difficulty tuning, we would love to get access to the data, and we can run it through the learner just as we continue to refine that process, and we're happy to share with you the results. And Luke and I are also on the ASPEN Dev mailing list, and we're happy to answer questions and help people as they adopt these new APIs. So that's all that I have. If there's any questions, my email address is there, or you can ask in the online forum, visit our website, and follow us on LinkedIn. That's all I have. Okay.
Thank you, Nathan. This is Thanh with ASPEN again. And I think we already done most of our agenda today. And I have two things that I want to correct. To say first is I had the typo in the subscribing. If you want to subscribe to the ASPEN Dev list, this is the correct email. Someone just told me. And secondly, I want to say that we excited to have all of you here. The YouTube stream showing upward 250 people at the same time at some point. Right now it's 226, which is, yeah. Thank you for watching. We plan to, we do have recording of this presentation. We will try to clean it up a little bit, and then you guys will receive a link to view it again. So our next session will be the same time, Thursday, 2 days from now. There will be two presentations, one from Quanta Technology about how they made use of this scripting engine for other application, and also we'll have another presentation by myself about the PRC26 application in OneLiner. After that, we will have a open forum, and if you watch my the email we sent, even if you want to ask question on Slido, you can just watch it like today. But if you want to do an audio and join us for the open forum, be ready for team meeting. Okay. Anyway, so thank you very much, and I hope to have you all back and more on Thursday. Thank you.